Hola y bienvenido, and welcome to my channel, which is teaching English with a focus on science and PhD students, etc. What I thought would be useful is to give you an idea of what I do when I'm not teaching English, so I'll give you an idea of my background in science and medical research. Let's get into it. Okay, so this was a presentation that I gave today, actually, and I thought I'd just record it for my channel and let you see what happens in the world of research. So small vessel disease is a syndrome, really, of different clinical and imaging findings in the brain. And here we can see an MRI of a brain with just a single slice through the brain, and on this side the patient has had a little stroke, that little bright white blob which I've just drawn over the top of, and this can be debilitating and lead to some weaknesses in the arm or face or speech, etc. And these types of strokes can be a risk factor for further strokes, perhaps more debilitating strokes, and they're also a common cause of dementia and post-stroke cognitive decline. So very relevant to study. I'm currently using this rather expensive Retinal camera to take pictures of the back of the eye, and got a few studies ongoing, but we'll talk about stroke studies today. And this camera can generate lots of different types of pictures, and these pictures can be processed and we can do analysis on the resultant metrics, and that tells us a lot about what's going on. And indeed, here's a large workflow that I'm responsible for. So this one single high definition retinal imaging eye camera can generate all these different types of images. And we get different measurements of vessels. These are the blood vessels in the eye. These are the tiny blood vessels that are too small to see with MRI, magnetic resonance imaging. So we use this retinal camera, and I'll talk today about this optical coherence tomography angiography, which is a non-invasive imaging technique that doesn't need any dye to be injected. And it's very new technology, very powerful. So a quick reminder on the anatomy of the eye. This is the front of the eye. This is the bit that you can accidentally poke with your finger, so be careful. But inside the eyeball at the back, it's got lots of these blood vessels, highly vascular, and this is the main area for light falling on the eye, and the images go back here to the brain through this optic nerve. The study that's ongoing is called Milestroke Study 3, and we're following patients across time. So we've got up to 180 patients at baseline, and these patients are coming all the way through, being followed up to 1 year. Recruitment is still ongoing, and follow-up is obviously ongoing as well. Why are we interested in the eye? Well, this is on the top row, you have 1, 2, 3, 4 images of the brain, different types of scans showing different features of small vessel disease and stroke, little holes in the brain, and little bleeds that show up black on this particular type of sequence. We have these white matter hyperintensities, which are quite common as you get older, and also in stroke patients. And this particular one is a little what we call lacunar stroke. So we're interested in the relationship between what's going on in the eye and what's going on in the brain. So 2 projects I'm giving an update on today. One involves retinal fluid and one's with the OCTA technology. So retinal fluid is these little black holes that appear in the back of the eye, and they split the nerve fiber layers, cause destruction. And what we can do is we can segment them and quantify them, and that's this bottom picture here. different types of fluid. We get these single isolated intraretinal cystic pockets, and we also get fluid, what we say perivascular, or around the vessels. And that's best appreciated on this next slide, where we have a vessel here. So that's a blood vessel, two blood vessels, one vein, one artery next to each other. And this is in cross section, so that's cutting through the vessel. You can see a vessel around there and here. And these little black dots, these are leakages coming from the vessel. So the vessel permeability and things leaking out of the vessels that should be staying inside the vessels. So our hypothesis for this particular study is that hyporeflectivities, so that's the black spots that we're seeing, of the retinal fluid, on eye imaging using this technology, OCT, is common. These hyporeflectivities are common in eye disease. So, for instance, diabetes and macular degeneration, and they can lead to vision loss, so they're very important to study. They're typically due to blood-retinal barrier dysfunction, but not many people have studied it in stroke and small vessel disease, and so we looked at the data in the first 106 stroke patients. We put together a little grading scheme where we can classify these findings as mild, moderate, and severe. And the main results so far is that these hyporeflectivities are seen in 25 to 32% of patients. And the proportion of patients with retinal fluid did not differ in those with comorbid eye disease compared to those without comorbid eye disease. And that was just a simple chi-squared test. But further, more advanced analysis, we used logistic regression. So this is a statistical technique that looks for a binary outcome, and by binary we just have either a 0 or 1, so presence or absence of retinal fluid. And we showed no findings in the right eye, but we did find higher white matter hyperintensity volume and higher basal ganglia perivascular space volume and count related to fluid in the eye. So that was a very interesting finding. But we also quantify these pockets of retinal fluid. And so because we have a quantification, we can use linear regression, and we showed that higher perivascular spaces, so this is a feature in the brain, associated with higher levels of retinal fluid in the right and left eyes. And these findings survived adjustments for various vascular and other risk factors that we call covariates. We ran lots of tests, so this tends to be called a fishing exercise, but the findings, we do have an a priori idea that perivascular spaces and leaky small vessels do contribute to small vessel stroke. And so it's interesting that these are popping up in relation to retinal fluid out of all the models that we studied. And just to finish up on retinal fluid, we have this black bit here is abnormal, it's pathological, and this chap at baseline had this pocket of retinal fluid in his eye. He was treated with anti-VEGF treatment, and we can see that this has resolved 1 year later. So if we can fix things in the eye, hopefully there's some potential at least to try fixing things in the brain. The second study I'll give an update on is OCTA. And this is a really new technology, and you get 3 different types of image in the one shot. An OCT structural image, and the fluid movement image is denoted by these yellow dots. It's quite interesting actually that the one in the middle is an overlay of both. So it's image 1, 2, and 3, and this one here just combines everything into the one image. And a word on the size, these little bars are just 200 microns, so 0.2 of a millimeter, very small. So we're seeing the smallest vessels in the human body. You cannot do that with MRI, so that's why this retinal camera is potentially very useful. And here's the technology by which it captures the image. It's a bit detailed, so I'm not going to go into that for this presentation. And these vessels are important because they supply what we call the retinal nerve fiber layer and also the ganglion cells. And they're very important for capturing the light that we see when we use our eyes and transferring the signal back to the brain to be interpreted. One of my students, Jun Fang, did, so she was from China, not a native English speaker. She did a very nice review of the literature, looked at 14 papers. Systematic review is a very good thing to do if you're a PhD student. And here are the main findings. We found that 2 studies showed an association between decreased vessel density and more white matter hypertensities in the brain. And 3 studies showed better cognition was related to better vessel density. So then we thought we will look at these parameters in mild stroke study 3. So stroke patients, and our aims were to look at retinal microvascular density and also the pattern that the vessels make and see what that might reveal about brain health. So here we quantified vessel density and fractal complexity from the OCTA data in the first 106 stroke patients. In terms of our findings, we found that vessel density and fractal complexity were reduced in patients with higher levels of various brain imaging measures of small vessel disease. However, only the measure of perivascular spaces survived adjustments for covariates, showing a significant relationship with fractal complexity in the right eye. And we're just about to publish this, hopefully. And here we can see that this one here was the significant relationship, so it's not touching this middle line, and that was perivascular spaces in the centrum semio-valley in the brain showed a relationship with a fractal complexity in the eye. So that's just a quick insight into the types of things that I can help you with. This presentation was given to people who already know about small vessel disease, but the point of putting it on my English language channel is to show what I can help you with. And just to show you that we can also do some fun things with this presentation software. That's it. I'll leave it there for now. If you're interested in language lessons, obviously it doesn't have to be as advanced as that. But if you're a PhD student and English is not your native language, particularly if you're interested in medical research, and it doesn't have to be the brain or the retina, get in touch and I can help you.